Hi everyone, welcome to this learning chat session with Jonathan Bootle today, who is going to present us the amazing Sumcheck protocol. Jonathan is a researcher at IBM Research Europe Zurich. He has had a PhD at UCL London. His work is quite extensive. He worked on lattices, hero codes, group signature a long time ago. He's one of the researchers that you should really look look for. So feel free to stalk him on Google Scholar or whatever other website you're using. And yeah, enjoy.
Well, thanks very much for the introduction, Raphael, apart from the stalking, maybe. So yeah, today the talk I'm going to give is called The Amazing Sumcheck Protocol. Okay, see if I can, I can change slides. And so the goal of today's talk is, we'll obviously go through all of these different terms in case anyone doesn't know them. Hopefully some people have a bit of familiarity, but the goal of today's talk is to explain like a low memory streaming version of Bulletproofs in terms of the Sumcheck protocol. So the title of the talk is The Amazing Sumcheck Protocol. This is like our final destination, explaining some kind of other protocol in terms of the Sumcheck protocol. But hopefully along the way, we're going to see some cool features and expose exactly what's amazing about the Sumcheck protocol. So yeah, I hope you enjoy. Is there anyone that doesn't have sort of any familiarity whatsoever? Like, for example, are there people who don't know what Bulletproofs is, for example? I just saw someone nod, but I don't know if it's so it's a nod for yes, you know about it, I hope. It's going to be fine anyway. I'm going to explain it, so it's all good. Okay, so the Sumcheck protocol and Bulletproofs are protocols in the setting of interactive proofs and arguments. So in this setting, of course, we've got an instance X and we've got a language L. And the idea of an interactive proof is for the prover to convince the verifier that an instance is in the language. So they're both going to exchange messages. And then at the end of the protocol, the verifier is either going to accept if they were convinced that the instance is in the language, or they're going to reject if they weren't convinced that the instance is in the language by the prover. And so from all interactive proofs, we want completeness. So if the instance really is in the language, the verifier should almost always accept. And otherwise, if it's not, we have soundness, and we want that the verifier should almost always reject. So there's going to be no zero knowledge in any of the talk today or any of the protocols. But all of the interactive proofs that we're coming up with will have a succinctness property. So we'll be dealing with proof systems where the proof size is much, much less than the instance size. And in some cases, we'll be aiming for proof systems where the verifier's work is much less than checking that the instance is in the language in a naive way. So the star of today's talk is the Sumcheck protocol. And the instance for the Sumcheck protocol is a polynomial P over a finite field F, a value U, let's call it like a target value in the finite field, and a subset H of the finite field. And the language we're considering is basically, we have instances in the language whenever a sum of evaluations of the polynomial over this subset H is equal to the target value. So yeah, summing up every variable over every different possible value in the subset H. And that's the language that the Sumcheck protocol deals with. And so the Sumcheck protocol is used like really all over the place. So I think it was first introduced in roughly like 1991 and 92. And then the motivation for using it at that time was to prove complexity theoretic results, like basically give interactive proofs that co-NP languages were satisfied or not. And it was also used to construct various different PCPs and other kinds of theoretical proof systems. And since then, maybe on the more practical side, there are a ton of succinct proofs and arguments based on the Sumcheck protocol. And this is like one family of arguments. And it's almost like whenever you have another family of Sumcheck protocols that gets designed, like another variant of the Sumcheck protocol, like the univariate Sumcheck protocol gives you a new family of succinct arguments. And likewise, with the Sumcheck protocol variant for tensor codes instead of polynomials, it gives you a new family of succinct arguments with new properties. So it's really, really nice. There are other people besides me who are fans of the Sumcheck protocol. Justin Toll has this great blog post on the unreasonable power of the Sumcheck protocol. And actually, in a way, I was kind of motivated by this blog post in giving this amazing Sumcheck protocol talk. And I suppose I want to talk about different properties that were discovered since Justin, or well, different properties that were explored more since Justin wrote his blog post. So other good things about the Sumcheck protocol are, well, the fact that it's got a time-optimal prover, very, very nice. One of the few protocols that's like that. Very strong soundness properties. That means you can make it non-interactive using the Fitch-Lemay heuristic, but with real hash functions and not with random oracles. So that's very good. And lastly, something that we're going to talk about a lot today, the fact that you can implement the Sumcheck protocol in small space. So with a prover that acts like a streaming algorithm and never has to keep too much of the input X in the head at any one time. And so the way that we're going to go through this talk is by examining connections between the Sumcheck protocol and other protocols. So one connection that's going to be important is the connection to split and fold protocols, of which Bulletproofs is an example. So the first one of these was introduced in 2016 in the discrete logarithm setting. And this was used to give various different types of efficient interactive proofs based on the discrete logarithm assumption, and then generalized to all kinds of other assumptions in cryptographic settings like pairings and unknown order groups like RSA groups or class groups, and even lattice-based arguments. And there are some unifying abstractions which connect all these split and fold arguments together. But yeah, essentially, Bulletproofs was a really popular protocol. There were lots of different implementations. There were articles with titles like this, and it was incorporated into a couple of different cryptocurrencies at least. And the start of this connection between the Sumcheck protocol and Bulletproofs is really to notice that Bulletproofs has a lot of useful properties. Split and fold arguments have lots of useful properties, which are the same as the useful properties of the Sumcheck protocol. So the prover runs in linear time. You can also implement some of these algorithms with a small amount of space, a streaming prover that doesn't use too much memory. Yeah, very, very similar. Very, very similar types of protocols. And so just almost by accident, with some other people, we stumbled on this connection between the Sumcheck protocol and different types of split and fold arguments, which previously appeared to be two different types of protocols. And we managed to show that they were both instantiations of a more general type of Sumcheck protocol that we called Sumcheck arguments. And that was a joint work with Alessandro Chiesa and Katerina Sotoraki. So we kind of collected all the Sumcheck-based things, all the split and fold-based techniques, and tried to show that they were kind of the same thing. So this kind of motivates the idea of using Sumcheck to explain a certain type of Bulletproofs protocol. We wanted to look at a streaming low memory version of Bulletproofs and explain its properties in terms of the Sumcheck protocol. So we have this connection. Now let's think a bit more about memory and what I mean when I say the protocol is low memory and has a streaming prover. I'll just pause here as well, just to take a drink of water and see if anyone has questions about the stuff that I've I've talked about so far.
Yeah, I do not see any questions so far. I actually do have one myself.
Yeah.
So among the Sumcheck, among the Sumcheck arguments, since I will use a generalization, what do you think would be one of the most interesting paper recently, and why?
One of the most interesting papers, did you say?
Yeah.
Oh, okay. Let's see. I think okay, well, the Sumcheck arguments paper that I've linked here is the one that explains the concept and tries to bring some of these things together. But if we think about the most interesting examples, then there's a paper called Dory by Jonathan Lee, and there's also this dark paper by Benedict Bunz and Ben Fish and Alan, whose surname I won't attempt. And these are interesting examples because they've got succinct verification, and not all of the other Sumcheck arguments have that property. So I would say it's the split and fold techniques with succinct verification that really stand out.
Yeah. I wanted to ask the question later, but since you started talking about succinct verification, one of the disadvantage for Sumcheck and Bulletproof is that the verification is let's say a bit slower than other schemes, and so I've started seeing more and more papers combining different proving schemes. And so basically using one to create an inner proof linearly, and using the other one to have a fast verification on the first proof. If you see
Yeah, okay.
Yeah. So for instance, I've seen combinations of core 16 and Stark, and I'm pretty sure there's going to be some talk about this in the Connect in a few weeks. And there've been, I said, blog posts and so on about this, and projects working on this. So do you think that this could also be done with some checks, or have you seen examples of this being done more particularly?
Yeah, I believe so. I don't see why not at all. I guess some of the nice features of these. Let me think. Yeah, it's definitely. I mean, I think it's definitely possible. I don't see any reason why you wouldn't want to do it. I guess I guess one of the things is like lots of the interactive proof systems anyway. They already seem to have a lot of some checks inside, and also the accumulator based approaches. I'd say they also bear some similarities. So I do think that there are these connections that are being exploited. Particularly with some of the folding schemes. Say they're very Sumcheck like in a way. So maybe not exactly Sumcheck, but definitely some stuff that works on similar principles.
Yeah, definitely. Yeah, I don't see any other questions, so you can continue.
Okay. Thanks. Yeah. Well, so talk about interactive proofs. So feel free to interact as much as possible. Please ask questions. It will be much more fun. Okay. So we've talked about the Sumcheck protocol and its connection to split and fold protocols a bit. We wanted to explain properties of Bulletproofs. So let's talk a bit about Bulletproofs and what it is and what exactly it does. So in this case, we have a commitment C, which is in a group G of prime order, and we have a commitment key, which is used to commit to messages. Differently from the Sumcheck protocol, the provers got their own secret witness, which is a message A, and the language here that we're trying to prove is that A is committed to using a Pedersen commitment and the key G. So C can be written as like the scalar product of the message A and the commitment key G. So it was shown in 2020 in this RRS paper that there's a streaming algorithm to compute bulletproofs where the prover uses a logarithmic amount of memory. Apart from this, other parameters of the proof are its logarithmic communication cost between the prover and the verifier, and the fact that it has a logarithmic number of rounds. So this is roughly what Bulletproofs looks like. And yeah, it was a very, very cool paper in 2020 with this streaming algorithm and this streaming fashion of computing the proof. The motivation for coming up with these streaming low memory algorithms for computing different proof systems, it's based on the fact that you might have very large amounts of like big, slow, long-term memory and only small amounts of very, very fast and short-term memory. So if you have, say, a witness and an instance for a proof stored on your hard drive, and then you have to load it up into some shorter-term memory in order to compute a proof, well, the extra cost of computing the proof might just be too much. There might be too much memory for your system, and then you might not be able to continue computing the proof on that basis. So there, you can try and think of different ways to get around this. You could run all of the operations for your proof algorithm and save all the results into slow memory, but that would just be really slow and irritating. So maybe a nicer thing to do is to imagine that the witness and the instance for your proof system are stored in slow memory, and you have a prover that's operating in a smaller amount of fast memory, and they have streaming access to the witness and the input and the instance. So they can read these, they can access the elements sequentially, and then they can make multiple passes over the witness and instance, and then compute the proof on the fly. And you won't get out of memory crashes when you try and compute your proof system. So not all proofs actually have this property. For example, Grot16 uses polynomial multiplication, which is done efficiently using fast Fourier transforms, and it's quite difficult, I think, or intensive. There's a lot of work on developing fast Fourier transform algorithms which work without using too much memory. So it's not an easy problem to design these streaming provers or low memory prover algorithms. So in this talk, we'll think about a prover algorithm which has, say, a logarithmic amount of memory in the length of its inputs and makes, say, like a logarithmic number of passes over the witness and the instance. And this all goes back to papers on streaming interactive proofs from 2011. So the reason I learned about this this paper from 2020 on streaming bulletproofs is that it has the potential to scale up succinct arguments. If you do have these streaming proof algorithms, and you don't have to worry so much about memory constraints. So if you think about the sizes of different circuits that you might like to prove, maybe some of these references are from old papers and people have found better circuits, but to compute a proof that you've correctly evaluated one SHA-526 hash uses 30,000 constraints according to this circuit computed in this 2014 paper. And actually, the typical limit that you could get up to on one machine is, say, using Grot16 proofs, or various other types of proof systems. Maybe you could compute proofs that you'd correctly evaluated a circuit with 33 million constraints or something like that, 2 to the 25. Maybe a bit more depending on your computer, but I don't expect it would be more than 2 to the 30. So the Milky Way is on there for scale, but we actually want to prove much more, like Filecoin Daily. At this link, you can check, and they say that they're computing, they're computing proofs, and they're proving stuff about roughly maybe 600 trillion calculation steps every day. This is not using one proof. This is like combining several different proofs together and aggregating them and composing them and so on. But we actually do want to be able to scale up our proof systems to prove things about extremely large statements. Otherwise, we're just going to crash and we're not going to be able to compute useful proofs. So it's fun to come up with proof systems that can handle these instance sizes. And there are different ways of solving these memory problems. One is just to try and use more machines. So I think the previous cutoff for that was around 2 billion constraints, using 20 machines to compute Grot16 proofs. Another method, which obviously scales massively, you can just keep going and compute proofs for really, really massive statements in these ways, is to use things like folding schemes or accumulators, or compose proofs together and give proofs that you've seen other proofs in order to compress things and continue proving a statement in many different steps. But one piece of work that I was involved in came up with these streaming prover algorithms, and we were able to scale our system to prove something about instances where n was equal to 2 to the 37 or 100 billion. This wasn't based on Bulletproofs, but it was really inspired and motivated by this 2020 paper, which showed that you could run Bulletproofs in a streaming fashion with this low memory prover. And that's sort of how I got interested in this paper. But this paper, BHRRS20, it actually came out and it was investigating these streaming properties before the paper with this connection between the Sumcheck protocol and all the split and fold techniques was published. So the reason I wanted to give the talk today was to kind of go back and revisit things and try and explain the results of this 2020 paper using this Sumcheck connection to Bulletproofs that only came along a bit later. So that's the goal for the rest of the talk. And so next I'm going to start getting into the details of the Sumcheck protocol and some of its different properties. So I'll take a pause here again and see if anyone wants to ask any questions. But please do ask questions, even the smallest question.
I'm sorry, you're too good of a speaker. Right now, there's no question yet.
Okay, no problem.
But they will come.
Sure. Okay. So these are the different things we'll talk about. We'll go into more details on what the Sumcheck protocol looks like, how you compute the messages and stuff like that. Maybe we'll talk about why it's secure, depending on how much time has elapsed. We'll talk about inner product arguments based on the Sumcheck protocol, because these are really directly analogous to what goes on in Bulletproofs, actually, according to this Sumcheck connection. We'll talk a bit about why these things are space efficient and can be computed with streaming provers. And then finally, I'll try and convince you that Bulletproofs is really a Sumcheck protocol in disguise. So I guess, yeah, I may end up skipping the security section in the interest of time, but I think, yeah, particularly the third section on inner product arguments and the last section where you see that Bulletproofs is really a Sumcheck protocol should be interesting, or hopefully a bit unexpected if you've not seen them before. So the Sumcheck protocol was introduced in 1992. We've talked about the instance for the protocol, which is this polynomial target and subset and the language. And what happens in the protocol is the prover computes this polynomial Q1, which is based on taking the polynomial and almost computing the target value, except that the prover doesn't evaluate the first input argument for the polynomial. They only sum up over the second value to the last value, and they just leave the first one free. So they almost compute U, but not quite. And then they send this polynomial to the verifier. So the verifier finishes off the calculation of the target EU, and then they pick a random value from the finite field and send this back to the prover. And this has the effect that the prover and verifier started off with a Sumcheck instance with the polynomial P and the target EU. And after the protocol, we've essentially reduced to a new polynomial, P prime, which is like P, but just evaluated at the randomness in the first input. And the new target value is Q1, evaluated at the randomness R1. So we've made progress here because we've reduced the number of variables of the polynomial by 1. And we've got this new instance, which satisfies this new Sumcheck property. And if we keep going and just do more reductions, then eventually, after all these reductions, we will have removed all the variables from the polynomial. And the final instance that we have is just checking that, well, this constant polynomial, p to the L, is equal to this constant u to the L. So the final instance is basically just checking a polynomial evaluation. Just checking that p evaluated at all these random points is equal to this, this single value. So if the verifier had wanted to check the original language in a naive way, then they might have had to evaluate the polynomial many, many times, like as many points as there are in h to the L, which could be really big. So even if we think of a small thing, like a small set like h is equal to 0, 1, then the size of h to the L is going to be 2 to the L. So from a potentially really large number of evaluations down to just 1 for the verifier. So that's the big advantage of using this protocol. And then if we look at the whole thing unrolled, then we have a kind of total description of the polynomials Qi that the prover computes and then sends to the verifier sequentially. Here are all the verifier's checks performed all together. And then the final instance that we get, essentially a polynomial evaluation. So we know the verifier makes a saving here, and the proof size is not too big either. If D is the degree of P, let's say the maximum individual degree in any individual variable, then the total communication in this proof is the number of variables times the degree up to constants. And the original instance size had quite a lot of coefficients. So the amount of communication in the Sumcheck protocol is much, much less than the original polynomial, and the verifier makes a big saving. So this shows that the Sumcheck protocol is really a succinct protocol. Okay, so I think I'll skip this. Well, I was planning to skip this discussion of like the security properties of the Sumcheck protocol. But maybe I'll just pause here, have a drink of water, and check whether anyone wants to see it.
Yeah, we actually have questions.
Mm-hmm.
So one Sam would like to know what polynomial scheme and opening scheme we can use for the scheme. Here you were only presenting the interactive version, and so we wanted to know also if we could use Fiat-Shamir to have non-interactive version. And finally, what would be the verifier cost for using the Fiat-Shamir transformation for the proof composition?
Let's see. Okay, so firstly, yes, definitely you can apply the Fiat-Shamir heuristic to this protocol. Actually, because of the properties, because of the way the soundness proof of the protocol goes, you have a strong soundness property called round-by-round soundness, and this makes it easier to analyze what happens with the Fiat-Shamir heuristic. So even though the protocol has a non-constant number of rounds, this round-by-round soundness property gives you a good advantage when analyzing what happens when you make the protocol non-interactive. I think for the second question, what commitment scheme might you use when you're using proof composition? Let's see. To be honest, I'm not too sure how to answer that question right off the bat. I might try and come back to it at the end, or if you send me an email or something, I can try and give you a better answer. But yeah, nothing comes to my mind right now.
Thank you so much. Thank you so much for your answer.
Okay, so let me skip forward a bit. I'm just going to pause and unpause my screen share and skip forward, and we'll talk about how to do inner product arguments using the Sumcheck protocol.
I have one question myself, if you don't mind.
Sure.
So here you are, if I understand what you are doing, if you can go back to the previous slides, you are doing P rounds because you are checking, you are evaluating each variable one by one.
Yeah.
So,
oops.
No worries. So my question was, would it make sense to, at each round, split the polynomial P into two polynomials of smaller sizes, like for FFTs, and so to evaluate several times at each round, so that you would have a fewer number of rounds, but of course, higher communication per round.
I'm sorry. Could you explain the splitting idea just once more?
Yeah, it's a bit like the same idea for FFTs and the K algorithm, where you would split P into two polynomials with odd and even terms. Of course, P would have to be a power of 2. And so you would have two polynomials, and 4, and 8, and so on, that you would evaluate at each round. But you would be able to evaluate more variables per round. So you would have fewer rounds of communication. So you would have fewer rounds of communication. But I guess memory-wise, it would be more expensive because you would have more polynomials to evaluate.
Yeah. Okay, I think I understand a bit better now. Yeah, I think you can do something like that. So, so what's happening in this protocol is so we have a sum that we want to check, and every time when the prover computes their polynomials Q, they're removing one entry from the sum. Now, really, like in full generality, this is a protocol where you have some expression involving like operators over many values, and so I think if you just stare at the expression for Q, you could leave like two variables, x1 and x2, free, and some of the rest. You could kind of strip off two operators at the same time if you wanted, and then change the verify checks accordingly. So there are all kinds of variations on this protocol if you want to reduce the number of rounds or do things slightly differently. You would end up with more communication if you did it the way that you said, because yeah, you'd have, at the moment we have like the queues have one variable and degree D. You'd be sending, yeah, I guess you'd be sending, yeah, they'd have maybe roughly D squared coefficients, yeah. But I think it probably works.
Thanks a lot.
Yeah. Okay, so let's skip ahead a bit and talk about space efficiency. Second. Just skipping through the slides. Okay, so let's talk about how to do inner product arguments using the Sumcheck protocol. And this is going to be, I guess this is going to be like directly analogous to the Bulletproofs protocol and discussion that we see a bit later on, just in maybe a slightly friendlier setting. So if we want to do inner product arguments using the Sumcheck protocol, now we're in the situation where the instance that we're considering will be two commitments, A and B, and an output U. The prover has two vectors, little a and little b, which are supposed to be the messages inside the commitments. And the prover wants to convince the verifier that A and B are really inside the commitments, and they satisfy the correct scalar product relation. So the Sumcheck protocol runs on polynomials. So straight away, if we imagine that we have polynomials available and think about polynomial commitment schemes, you can imagine the polynomial commitment scheme involves like maybe some key generation. But once you have a key, you can commit to a particular message polynomial. We have some binding property, which means it's difficult to find two messages which give the same commitment. But the most interesting thing about polynomial commitment schemes is an evaluation protocol, another interactive proof, so that if you have a key and a commitment to a particular polynomial and some inputs and outputs, then the prover can convince the verifier that that basically they know a polynomial inside the commitment which satisfies the correct input and output relation. So let's change the goalpost slightly and imagine that we have polynomial commitments, capital A and B, to the vectors A and B, and we want to prove this scalar product relation. So what we really need now is a way to go from this scalar product relation that we want to prove into something to do with polynomials, and also a sum relation on polynomials, because we've got the Sumcheck protocol that deals with exactly that kind of thing. So what we need to be able to do is interpolate A and B and consider the polynomials PA and PB with exactly the same coefficients as the vectors A and B, and then we'll be able to get to like a proper polynomial representation of this scalar product. So we can consider Lagrange polynomials in one variable, and multivariate Lagrange polynomials as well. And the point about these is that whenever you have a binary x which is equal to the index I, defining the Lagrange polynomial, then the polynomial is going to output 1. And otherwise it's going to output 0, which you can see kind of just by direct calculation. So if we have a particular vector and we consider the entries I of the vector in their binary decomposition, then we can get polynomials using these Lagrange polynomials, which just exactly interpolate the vector v over the finite field. And whenever you put in a particular binary input, which is like the binary representation of index j, then you get vj as the output. So Lagrange polynomials are like, they're not too difficult, they're not too bad to deal with. The reason I sort of display them here is to prepare you for a bit of generalization later, where we deal with polynomials that might not be so familiar.
To compute these polynomials, you would have to use, I guess, IFFTs, and so the cost would be superlinear, be n log n.
So that's not the case actually. So because they have this nice structure. So when, let's see if I can write on the screen. I don't know if you'll be able to see me, but depending on the value of I, you either get this term or this term. When you want to evaluate a polynomial like this, you can actually, because you have x1 appearing in many different terms, you can sort of split the sum according to whether the first bit of I is 0 or 1. And then there's a nice sort of tree-like algorithm for computing this, which takes linear time in the end. So this is actually much more efficient than if you were using univariate Lagrange polynomials. You'd probably get an n log n there.
Oh, perfect. And I also had a question just before, but I didn't have the time to ask it. Do you need any specific properties for your polynomial skill, such as some homomorphicity? The polynomial seems to be homomorphic for the addition or something else.
The polynomial commitment schemes.
Yeah.
No, you don't need anything. They're just used to prove that the evaluation is done in the end. Now, we're not considering zero knowledge today. If you wanted to add zero knowledge, it would be easy to do that if the polynomial commitment schemes were homomorphic.
Yeah.
But yeah, in this simple setting, you don't need anything like that at all.
Thank you.
Okay. So these polynomials have a value d equal to 1. So the maximum degree in any variable is 1, and like a log n number of variables if we want to interpolate something with n entries. Oh, my annotations are still on the screen. Okay, so if we want to give inner product arguments, what we can do is use these polynomials to interpolate a and b, and take the expression involving scalar products. Observe that each entry of a vector is given by an evaluation of one of these interpolating polynomials. And then if we take the product polynomial of the two, evaluate that at any binary input, we get the product of an entry of A with the corresponding entry of B. And if we sum all these up, this is the same as computing the scalar product of A and B. So we can rewrite the scalar product of A and B equal to U as a sum of polynomial evaluations. And then we have a protocol just for checking that. So we can start by running the Sumcheck protocol on the product of PA and PB. Now, at the end of the Sumcheck protocol, what the verifier wants to do is check an evaluation of the polynomial at a random point. So in this case, the polynomial we were using is PA times PB. This is actually hidden from the verifier since the verifier is only seeing these polynomial commitments and not seeing PA and PB, which only the prover knows. So the prover has to help the verifier out just a little bit by sending the evaluations of the polynomial to the verifier. And then the verifier can do the final check in the Sumcheck protocol, and they can prove using the polynomial commitment scheme that these evaluations were done correctly with respect to the commitments. So as soon as you have polynomial commitments, you can prove lots of different types of algebraic expressions, like as well as just inner products, just using the Sumcheck protocol to reduce to something that you can then check using the evaluation protocols in the polynomial commitment scheme. And then the cost of this is fairly good. The degree of the polynomial p is 2, a constant, and we've got log n variables, so we're going to get O of log n proof size from the Sumcheck protocol, sending like constant size polynomials over logarithmically many rounds, plus like whatever the cost of the evaluation proofs are. Okay, now we're going to return to this later, and the setting is going to be slightly different. So, is there any part of this which seems strange or like doesn't make sense?
It seems all good.
Great. Okay, so now let's talk about why the Sumcheck protocol is space efficient. And this all build up to a finale, basically. We're going to show that the Sumcheck protocol is space efficient and that there's a streaming method of computing that with a low memory prover. Then as soon as we see the Bulletproofs can be expressed as a Sumcheck, then just sort of instantly for free, we'll kind of understand that Bulletproofs type protocols also have low memory streaming algorithms to compute their proofs. So let's see how this space efficiency works. So what we need to do in the Sumcheck protocol, if you know something about Bulletproofs already, then you might see some connections or analogies here. But in the Sumcheck protocol, because we're reducing gradually to smaller and smaller polynomials, where we just evaluate the polynomial that we start with, say at more and more random inputs, then we need to prove that it works for the first step of the Sumcheck protocol. If we can compute, if there was a way to compute the first message in the Sumcheck protocol using a small amount of memory, and there was a way to generate the next polynomial in the Sumcheck instance, so this p prime where x1 was evaluated at r1, if we could stream that based on the initial polynomial, then we could do something recursive. So if we have a low memory algorithm for reducing one step, we can combine it with the same algorithm to get low memory algorithms for producing the next steps. So first, let's show that we can produce like witness polynomials or polynomials for the Sumcheck, and we can reduce the instance in a low memory fashion, given that we only have access to the original input, which is in this case a vector A, and like I guess also a vector B, but I'll just show the case for A here. So if we kind of evaluate things and look at what we get in the end, when we evaluate this interpolating polynomial for A in the first input argument, we basically get a sum of n-2 things, and we've collapsed pairs of values together. So we've collapsed, say, like A0 and A1 together by taking a linear combination with R1, and we've collapsed A2 and A3 together, and A4 and A5 together, and so on and so forth. So given access to a stream, like a sequence of elements of the vector A, we need to be able to compute the coefficients of this polynomial. And so obviously we can. If we have access to A as a sequence of elements, the calculation that we want to do just looks like this. And if we want to reduce further rounds in the Sumcheck protocol, then we just need to collapse those together as well. And then at some point at the end of the protocol, we will have collapsed everything down to a single value. So this is how you compute like reduced instances for the Sumcheck. And if you want to stream these, you just need to do everything given sequential access to the entries of A. So you could take the first two entries, compress those into something. You could take the next two entries, compress those to get a stream of the vector A prime. So you can do this in a linear amount of time, a constant amount of memory, and just one pass over the input A. And similarly for collapsing the next instance down to get the next polynomials for the Sumcheck protocol. And so when we add all this up, like overall, just for compressing the instances of the Sumcheck protocol in a low memory way, we're going to get something which is overall a linear amount of time, a logarithmic amount of memory needed, and just one pass over the input vector A. And then when we actually want to put this into the scalar product argument, say we have access to inputs A, B, like now we know that we can always stream polynomials P sub A and P sub B evaluated at some different input arguments in a low memory fashion. So we can generate streams like that. And we want to compute a polynomial which looks like this. So like a sum of different polynomial evaluations in all the later input arguments. So we can we can actually compute this incrementally. So if we want to compute Q1 in an evaluation basis, maybe not in terms of coefficients, we could compute Q1 evaluated at various different points. We could use the evaluations of PA and PB, which is just the same as the entries of the vectors A and B, and we could do some operations on those and sort of incrementally compute the polynomial Q1 using a few elements of the sum at a time. So just gradually building up to that and computing it in an incremental way. We've also seen from the previous slide that we can get like new compressed input vectors A prime and B prime, which are like the instance for the next round of the Sumcheck protocol, we can generate streams of those based on streams of A and B. So similarly, we can like incrementally compute the next message in the protocol from the streams of A prime and B prime, and so on and so forth until we get to the end of the protocol. So to generate reduced polynomials where we've partially evaluated from the inputs A and B, that takes O of 1 time, O of log n memory, and O of 1 passes from the previous slide. And over the course of the protocol, we want to compute the first instance, the second instance, and then finally the log nth instance. And incrementally computing these QI polynomials from these reduced instances is again a linear amount of time and a constant amount of memory here and passes. So if we total all this up, we get a streaming prover algorithm for computing all the messages in this protocol, and it uses O of n log n time, a logarithmic amount of memory at any point, and it makes a logarithmic number of passes over the inputs to the protocol. So there's one pass for every round of the, well, O of 1 passes maybe for every round of the Sumcheck protocol. So
Yeah.
yes, how's all this so far?
No complaints so far, unfortunately.
Okay, I see that we're coming up to the end of the hour. It will go a little bit over that, but yeah, we're almost at the let's say the punchline or the payoff where we can get some streaming properties of Bulletproofs basically for free. So yeah, we may take 10 minutes or maybe 15 longer past the hour, I think, but not too long.
Yep, don't worry about this.
Yeah. Okay, so it's a proud moment where I can try and convince you that Bulletproofs is actually just equivalent to a very strange type of Sumcheck protocol. And then we get all these space and streaming properties for free. So let's consider the original Bulletproofs method. In the original, let's say the original source of this type of protocol, the prover wants to convince the verifier that they have a message which opens a commitment, so this inner product relation. And the protocol proceeds by splitting the message A into a left part and a right part, computing some cross terms where the left and right parts of the messages and commitments are combined, just left to right and right to left, sending these commitments to the verifier, and then the verifier responds with a random field element as a challenge. And so this has the effect of reducing the instance, just like in the Sumcheck protocol. We've reduced the message to a linear combination of the left part and the right part, which is only half the length of the original. And we've reduced to a new instance as well. So the new instance, which should be C prime, is a combination of the minus commitment and the original commitment and the plus commitment. And we've got a new commitment key, which is also half the length because it's the left and right combined as well. And these are supposed to satisfy a new inner product relation. So the Bulletproofs protocol is for reducing problems about computing these Pedersen commitments to problems of half the length. And if you do that over and over and over again, you eventually get a commitment, which is sort of trivial. It's just a group element where you've only committed to a one element message. And then at that point, the prover could easily send it to the verifier. And then the verifier could just check. So this is a big saving over sending all the elements of the original message A, because we've only sent 2 elements in every round, and it takes log n rounds to halve the length of the message down to just a constant. And in the end, what we get is a verifier time, which is logarithmic just for doing all the calculations on the C's, and we get a linear verifier cost for computing this final commitment key GL. So this is what Bulletproofs looks like. And now I'm going to show you a different thing, which solves the same problem, but is based on the Sumcheck protocol. Okay, so if we've got a Pedersen commitment, we know that a Pedersen commitment is a sum of products, and I've been writing C equals A times G. So I've been writing this Pedersen commitment as a scalar product. So this is a scalar product of a field element vector and a group element vector. Now we've already seen that the Sumcheck protocol can give us things for reasoning about scalar products over, well, scalar products of two vectors over finite fields. So maybe someone can give me a guess as to what we should try and do to give a proof related to these Pedersen commitments, since we know they're based on scalar products. So someone from the audience, give me a hint. Otherwise, Raphael's going to have to do all the work here.
Please, anyone? Ray, do you want to say something?
Yeah, the answer is always Sumcheck, indeed. So
I want to say about Pedersen commitments, but it's not important too much. I want to say, yeah, it's Sumcheck. Okay.
Yeah, of course it is. The whole talk is about how amazing the Sumcheck protocol is. Obviously, it's amazing enough to deal with this situation too. Now the difference is here. I guess that should be a capital G. But instead of thinking about polynomials and interpolation over finite fields, now we've got this scalar product, which is defined with a field element vector and a group element vector. We just need to think about defining polynomials over groups, and a polynomial that can interpolate the commitment scheme over the group. And so, like, as soon as you can reconcile with the idea of defining polynomials that work over a group of prime order, then you can just run the same kind of Sumcheck protocol as before. And this is almost the same as what we've seen, but it's not quite the same. And the reason is that with the original scalar product protocol, so the prover knew the vectors A and B, and then was evaluating both of those polynomials for the verifier and sending the evaluations. This time, the verifier knows the commitment key for themselves as it's part of the instance. So the verifier can evaluate the group element part of this polynomial at the end of the Sumcheck, and they only need the prover to help them with the A part. In fact, it's important for the soundness of this protocol that the prover evaluates the A part, but the verifier actually evaluates the G part for themselves. So the proof size is, well, okay, we've done a Sumcheck with a quadratic polynomial. Quadratic polynomials in one variable have three coefficients. So initially it looks like the proof size here is 3 log n. There is a way to optimize it down to 2 and get something with the same communication complexity as the Bulletproofs protocol for the previous slide. And the cheap operations from the verifier, the log n operations, when you compute the new C values in Bulletproofs, correspond to all the Sumcheck verifier checks. The expensive operation for the verifier from the previous thing, where they were folding up the commitment keys smaller and smaller, that corresponds to an operation where they evaluate this interpolating polynomial in the commitment scheme. So all the costs, everything, the communication, corresponds really exactly to what was going on in the Bulletproofs protocol. And we discovered this kind of by accident. And up to a change of basis, we discussed this in our paper on Sumcheck arguments. And just in case anyone's nervous about the idea of polynomials over a group, then really everything's much the same as before, except, well, when we want to evaluate a polynomial over a group, the evaluation points are always field elements. So these Lagrange polynomials that I'm going to draw a circle around, when you evaluate those at field elements, you just get field elements. And if you multiply those by group elements, but then we're just going to have scalar multiplication between group and field elements. So, so it's really fine to define polynomials over groups like this. Nothing goes wrong, and the protocol just works out fine. So let's see. So I had some slides on the soundness of this protocol, which I'm going to skip. I'm just going to explain what kind of soundness guarantee it satisfies. Because with the Sumcheck protocol, the original one, with the classic Sumcheck protocol, the prover and the verifier both know the polynomial P. So we've got a soundness question. Does P sum up to give the target value, or does it not? But it doesn't make sense to ask those kinds of questions with Pedersen commitments, because any group element actually has an opening as a Pedersen commitment. In fact, there are lots of different messages, lots of different message vectors, which will produce a particular Pedersen commitment from a certain key. So there's no point asking if the instance is not in the language. It's always in the language, because there are always messages that open a commitment. So we need to consider a knowledge soundness notion, where we have a knowledge extractor that, given access to certain protocol transcripts, is able to extract a valid message opening to the commitment. So I'm just going to pause here and skip the rest of the soundness argument, and then we'll kind of finish up and summarize. Skip. Okay, so given this connection between Sumcheck and Bulletproofs, it's really easy to design different variants of the Bulletproofs protocol now, and to see where different types of work come from. So if I were to build up a correspondence, the polynomial we used in the protocol just now interpolates with Lagrange polynomials. The one, and it has the set 0 and 1 used in the Sumcheck. And we compute the scalar product in this kind of fashion. Whereas in the original papers that introduced split and fold techniques leading up to Bulletproofs, we used the polynomial in the monomial basis instead of Lagrange. The set that you would have to use would be -1 and 1. And you have to make some adjustments, like you have to put the group element vector in reverse order. And then the coefficients of the polynomials in the Sumcheck come out to be exactly this C plus and C minus from the Bulletproofs protocol, or at least the 2016 version of the protocol. So the actual Bulletproofs protocol proves things about combined commitments, where you have a single group element committing to A and B and the scalar product. And with the Sumcheck view, it's really easy to see what you should do to come up with a split and fold protocol for this type of commitment. You should just have one polynomial that produces the first scalar product, add it to one polynomial that produces the second scalar product, and then we have like a third component which produces the scalar product of A and B. So if I messed around with the polynomial bases and the set H enough, I would be able to recover the original Bulletproofs paper as a type of Sumcheck. All the messages would be the same and everything like that, just we'd have written the protocol in a different form. And similarly, if I want to come up with a polynomial commitment scheme, the evaluation of a polynomial whose coefficients are a vector A, well, the evaluation is equal to the scalar product of A and an expansion of all the input values into various different types of monomials. So I could come up with a polynomial commitment scheme by running a sum check, like one to produce the commitment and one to produce the polynomial evaluation. And basically, since the Sumcheck protocol has these amazing streaming properties, any of these protocols that we produce as Sumchecks, for different types of commitments, different types of proofs of knowledge of openings of commitments, they're all going to have the same kind of memory efficient and space efficient properties. So this was proved kind of from scratch in this BHRRS 20 paper. But given the Sumcheck connection, you can sort of see it straight away, and it explains their results in a different way. And you can extend this to lots of other different types of commitment schemes under different types of cryptographic assumptions, which we do in the paper, so including based on lattice assumptions. Okay, so I'll just summarize the stuff that we've seen. We've seen what the Sumcheck protocol is. We've seen some inner product arguments, how they can be computed in a space-efficient way. Finally, we've seen that Bulletproofs is a very particular type of Sumcheck. The polynomials happen to be on groups instead of fields, but that's it. And thus, it's going to inherit all these nice space efficiency properties, basically because the original Sumcheck has them. And I think some really nice extensions of this come with applying the same techniques to different families of Sumcheck protocols or different types of split and fold protocols. For example, we saw that the scalar product protocol had a low memory prove-out algorithm, but for different varieties of Sumcheck, like the Sumcheck for tensor codes, we don't really know a whole lot about the streaming properties of these protocols. And actually, it's hard to encode using some of these error correcting codes in a streaming fashion. So it would be really cool to have some low memory protocols based on these Sumcheck variants as well. This would give us some time optimal low memory proofs based on error correcting codes. They would work something like Fry proofs or Starks, but with, let's say, asymptotically more efficient error correcting codes. And another way to go would be to try and show that techniques used to make the Sumcheck protocol non-interactive without relying on the random oracle model extend to split and fold techniques like Bulletproofs. So maybe using the Sumcheck connection, there's a way to do that. So I guess going back to the start of this talk, I wanted to try and convince you that the Sumcheck protocol is really amazing, and hopefully I've done it, because at the time when we came up with these discrete logarithm split and fold arguments, we had no idea that they were anything to do with the Sumcheck protocol at all. It was a really surprising fact that we discovered almost by accident. And then still there were other papers coming out, like this space efficient one, or other papers proving properties of these split and fold arguments. And then some of them have turned out to be really closely connected to the properties of the Sumcheck protocol. So it's sort of amazing that we kind of rediscovered that protocol in a different format. And I hope I've managed to convince you that this is at least a little bit surprising and amazing. Thank you very much.
Thanks, Aljan. Sorry. Thanks, Jonathan, for this talk. It was great. I at least think that that the Sumcheck protocol is awesome.
Great.
I can see a few people clapping here and there. I'd like to ask if any participants have any final questions for Jonathan.
Is it
yeah, sorry.
It's okay, I'm reading it. So
yeah.
Is it the split and fold of Sumchecks, or is it that both these classes of protocols follow a divide and conquer paradigm? Good question. So I think the Sumcheck one, the split and fold ones, most of the protocols that we've seen using the split and fold techniques, you can basically interpolate the different messages in those protocols. You can almost always do this kind of interpolation and then get a Sumcheck interpretation of the same protocol. So far, I guess haven't seen. I guess using interpolation, you can sort of interpret most split and fold protocols in that way. I think what's really interesting is if you do get divide and conquer protocols, which are less algebraic, that you can't do that interpolation thing on, and you can't see them as polynomials or codes. So far, most of the ones I've seen, they can be turned into Sumchecks, whereas the divide and conquer class is sort of broader, and it doesn't have to be based on this algebra related to polynomial evaluation. So I think an example where you can see that is so Abiram Kotapali is one of the authors, and I think the other one is Brian Pono, and they have a paper on tensor reductions. And I think those tensor reductions are maybe an even broader class. So yeah, if you're interested in different protocols and how they fit into the framework, I think it would be interesting to find a divide and conquer protocol which is a tensor reduction, but which is not expressible as some sort of Sumcheck protocol. Fry maybe. I think you could probably express Fry as a Sumcheck, because again, it's very algebraic. I mean, I think some parts of the verifier's check you would have to interpret differently, but ultimately the folding procedure is very, very similar. So I don't think it would be exactly the same. Maybe not such a neat correspondence as for Bulletproofs, but yeah, I'd be willing to bet you can come up with a very Sumchecky interpretation of Fry.
Yeah, I don't see any other question. And actually, I have to think to a few things you said before I can ask the question myself. And it will be offline for sure. So thanks a lot, Jonathan, for this talk. It was amazing. And yeah, I guess we can say have a good day and talk to you. See you later, hopefully.